Okay, so the last time we were talking about, so it's been a week since it was actually possible. So I'll take you through some of the examples, or some of this detail we had before. We looked at some ideals here. Really the theme of what I'm trying to do is I want to convince you that there are ideals that are invertible without being principal. So we've gone over this business that, you know, all principal ideals are invertible, non-zero principal ideals, I should say. So I looked at these three ideals. So I won't go over the details that I think I've established, and we can pick on them. Maybe do it. These very basic number theory showed that this one was in fact a proper ideal. These two, it's the same kind of thing. And we'll take it a step further. None are principal. And I'll kind of take you through that quickly. Fine. Well, let's suppose it was. And so to then this is generated by some single element x. And so notice that x must divide 2 and x must divide 1 plus radical -5. Right, because the principal generator has to divide both of these things. Now, recall, if a plus b radical -5 is in and the norm it almost reminds me of being in high school. Remember how you had to like rationalize denominators and you multiplied by the conjugate. And it turns out that the norm has some properties, which I did skip over, but if anybody protests, I can go over this in more detail if you like, but the norm of alpha beta this is an exercise in quadratic forms, or easier, it's an exercise in Galois theory, actually. The norm of alpha is 0 if and only if alpha is 0. And this is kind of a cool one. The norm of alpha is equal to 1 if and only if alpha if and only if that animal is a unit in there, right? Actually, it's supposed to be plus or minus 1, but I threw it minus 1 because no way that's ever being minus 1, is it? So in particular, if x divides 2 and x divides 1 plus radical -5, then 2 equals xc and 1 plus radical -5 is equal to xy, let's say. And this gives, if I take the norm of both sides, this is the utility of the norm. the norm of 2 is 4, right? Using that first property, and the norm of 1 plus radical negative 5 is 6. So norm x is a common divisor of 4 and 6, right? And of course, it's an integer, right? The norm always turns out to be an integer. And the only common divisors I can think of 4 and 6 are 1 and 2. This would give an immediate contradiction, because that would mean that x is a unit, which would mean that the ideal 2, or 2, 1 plus radical negative 5 is not proper, which we've already shown is proper. And norm x equals 2 is another contradiction, because 2 is not achievable as the sum of the square and 5 times the square. So none of these are principal, right? Obviously, I just checked one, but the proof for the other ones are very, very similar. Now, check this out. If you look, if you look at the product of these two ideals, this is generated by 4 product of these two, I guess, which is minus 4. Are you okay with that? And that ideal is principal. That is the ideal generated by 2. Now, let me point out that this containment, that one's pretty straightforward, isn't it, right? Because certainly 2 divides every one of these generators, right? So the big question is why is 2 in here? But notice, if you take this one minus this one, so subtract dude comes in and takes this away from this, you get 6, don't you? And now once you got 6 and 4, you've got 2, so you get this containment and you get equality. But this, you usually don't expect this to happen for ideals, right? I mean, if you look at a polynomial ring in 2 variables, the ideal generated by x and y, if you square that, it's generated by x squared, xy, and y squared, and there's no shortcut to those 3 generators, right? But this one collapses all the way back down to a principal. By the way, let me look at some of these other ones here. What happens when I multiply these two ideals together? This is 9, 3 minus 3 radical negative 5, 3 plus 3 radical negative 5, and 6. This one's actually easier to pick out. This is the ideal generated by. Certainly 3 divides this, and so give the difference of these 2. What about this one? What happens if, is that what I want to do? No, I do not. What about this one? I mean, I could do that one. This one's principal as well. Actually, let's do that. So I'm gonna this one is 6. 2 minus 2 radical negative 5. 3 plus 3 radical negative 5. And 6, again, so that's redundant. Right? Now, I really don't know what the answer is, but I know almost what the answer is. Can anybody help me out with, what this one is here? I know.
By 2 and 3. Quadrat, I don't know.
What was it?
Just guessing.
Oh, so what you guess?
The generated by 2 and 3.
Yeah, but that would be everything, wouldn't it?
Like 6. 6.
No, because 6 certainly didn't divide these two. On the right track. I think this is.
1 plus minus.
I always get this confused. I never can remember whether it's plus or minus, but I think it's this one. Certainly, certainly, let's check first this containment here. Certainly this divides 6, doesn't it? I agree, because this times its conjugate is 6. And certainly this divides this one. What I don't know is, this, right? Well, let's see. And yes, I am going back to high school.
Oh, no.
Right, seriously, here I am in high school, let's divide this out, what would you do? That's right, you multiply by the conjugate here. And this is going to be, I can pull 3 out of this, it's gonna be 3 times 6. So yes, it does. Okay. Because this divides all 3. Now, the other containment, right, I need to show that this thing is in here, so how do I get it?
You add the two inner generators, and then you subtract that from 6.
Minus this plus this, right? Minus this plus this and add them together. Because what I'm trying to do is get my tail right, right? If I go minus this, minus this, minus this. Minus, minus. So that's going to be minus radical negative 5, right? Minus 3 times this, plus 2 times this. And then I'm gonna have a minus 3, minus 2 is minus 5. And now add 6 to it. So I get the other containment as well. Everybody okay with that? Well, maybe you can save me a little trouble here. What's this one going to be?
I think that's 1 plus radical negative 5.
It is, because this is right here. Because P2, we showed last time, is its own conjugate. So this is P2, P3 conjugate, conjugate. which is, right. Which is the conjugate of this one, which is 1 plus radical. Everybody agree with that? Okay, so what's the point to all this? Well, notice that all these ideals are invertible, right? P2 squared is principal. So P2 is invertible. We showed last time that if you have an ideal I and you multiply it by another ideal J, non-zero, if you get a principal non-zero ideal, then the original ideal I had to be invertible, right? Is principal. So P3 is invertible. And P2, P3 bar is principal. So P3 bar is invertible. Now, I'm going to give you a little extra. So why do we care about invertible ideals? Who cares? Well, because they help recover loss of good factorization sometimes. They help understand it. So this is kind of a peek ahead, and we're going to get to this after that. Yes.
One question, the definition, invertible has something to do with the, like, certain structure where you are like multiplying ideals, something like that? Or why is all invertible possible?
Oh yeah, I'm going to introduce the class group here in a bit. Yeah, but do you remember the theorem that said that an ideal is invertible if and only if you can multiply by non-zero ideal and get a principal non-zero? Okay. So okay, show of hands. How many of you folks in your past, in a number theory class or beginning abstract algebra class, saw this as kind of a canonical first example of bad factors? Right. This is a classic. Everybody loves it, right? It's like Bob Hope or something. Everybody loves it. So this is bad factorization of elements. 2 times 3, both irreducible. This times this, both irreducible. And by the way, does anybody remember, from an ideal theoretic perspective, what does it mean for an element is invertible if and only if the principal ideal it generates is? Anybody remember what it was? An element is irreducible. That's invertible. An element is irreducible if and only if the principal ideal generated by that element is maximal among principal ideals, right? So it doesn't get any bigger among the proper principal ideals. And that's what happens here. We have bad factorization among principal. This is as big as possible principal, so is this and these two, and they factor together in a wonky way. But check this out. If you consider these to be ideals, this is P2, P2. What 2 is, and this is P3, P3 bar. And this is just a shuffle job. So this right here is, I'm already going to get this wrong. This is P2, P3. And this is P2, P3. And so notice, at least it appears in this example, that even though these principal ideals are screwed up in the sense that you've got different ways to represent these into a product of maximal principal ideals, this is unique. It's just a rearrangement, because of both these factorizations, I get the prime ideal P2 twice, P3 and its conjugate. Right. So in a certain sense, what seems to be going on here is, even though the elements don't factor uniquely into irreducibles or primes, the ideals, and we'll get to that later. Okay, any questions? All right, yeah, okay. Definition. Won't quite talk about this, but I'm gonna introduce this, very important, mathematical structure that is used in number theory, and algebra quite a bit. Let, INVR is set of I, such that I is an invertible ideal. And it's of R, not in R, so this is all the invertible ideals. Now, the invertible ideals actually form a group. Well, I'm gonna write this down. Somewhere, add to this definition. Print R, this means principal, is the set of omega R this is the set of principal fraction. Um, in that definition there, and make some remarks and add to it. Notice that INVR is a group. And this is grouped under multiplication of ideals. Note that the operative thing here, this is very easy to check. If you have I and J, it is easy, so these are both invertible ideals. It's easy to check that IJ inverse is I inverse J inverse. So IJ is also in because the inverse of IJ is I inverse J inverse, and if I inverses R and JJ inverses R, then IJ is also invertible. Of course, the identity of this group would be R. Good. The associativity is easy, and of course, the inverse, already got that.
Is it a billion?
What's that?
This is a billion, right?
Absolutely, this is a billion because, of course, we're talking about commutative rings here. And the collection of principal invertible ideals is certainly a subgroup, right? Because notice that, if, omega R times eta R is omega eta R, which is still principal, which is all known, and it's pretty easy to see what the inverse of that is. This is a subgroup, right? Now, in general, you would think that this would be what we would want. I care about the group of invertible ideals, principal ideals. Here's the problem. There's a lot of noise in this, right? I mean, just take a ring like the integers, right? Print R, it already is humongous, right? Yeah, I mean, print R is essentially, what is print R? It's basically the non-zero elements of Q under multiplication. That's what print R is for the integer. That's a big group. And what is the invertible ideals, the integers? Well, every ordinary ideal in the integers is principal, isn't it?
So it's every fractional ideal.
That is correct. Every fractional ideal must be principal as well, because fractional ideals can all be knocked down into a ring by multiplication by a non-zero element, right? So in the integers, so here's what you have in the integers, right? What a mess. The invertible ideals, non-zero elements of Q under multiplication, principal ideals, same thing. So oftentimes, what are the domain class group R is this is the idea. Group theorists love to do this, right? I mean, the principal ideals really don't give me a lot of useful information. They're just a bunch of principal ideals just clogging up the words. They're like, I don't know, a new card reader on a classroom door for no reason, right? And so what do? We mod out by these to sort of measure. Let me give you a quick observation here. No. If on is a PID, then CL on is big. So in other words, this little measuring stick, at least for some domains, so if you're a PID, this comes up to be right? Why is this true? Well, let R be a PID and I an invertible ideal of R. Well, there exists an element, A and R, such that AI is equal to, or I'm sorry, AI is contained in R, right? Well, so now I've taken my invertible ideal, I put it inside the ring, so now it's an ordinary ideal. So AI is X bar, some I is A inverse X R. So any element of I and VR turns out to be principal, so all cosines are trivial. Or equivalent to trivial cosine. Okay, any questions on that? Yes. Okay. This is one of my favorite theorems. I'm digging on this theorem a lot. I just think this is really pretty. Um. Uh. Let R be a domain and I an invertible ideal. And I is finitely generated. This is a wonderful theorem for a couple of reasons. Number one, just from the definition of what it means to be an invertible ideal, I inverse is equal to R. It is not clear at all that finitely generated is a necessary condition. This says it is, right? We're going to see why. Let me give you a caution though, even though I'm a big fan of this theorem, the other direction is wildly untrue. If I walk up to you on the street and give you an ideal that's not finitely generated, it's pretty, or if I give you an ideal that's finitely generated, if it ain't principal and you're not in a very special type of domain, then it's very unlikely that it is invertible. Invertible is a pretty strong.
When you say finally generated, you mean as a R module?
Yes, it's an R module. Uh, whoops. That will make the perfect. Consider our invertible, ideal I. What does it mean to be invertible? I versus R, right? Now, of course, recall, and maybe I'll scribble those here, real quick. Recall that I inverse is a set of omega k minus 0. Oh. Such that omega I. What does it mean for I inverse to be equal to R? Well, of course, I inverse is also another fractional ideal, but it's a subset of R. So this sucker right here is an ideal in R. Everybody agree with that? And what we're saying here when it's invertible is not just any ideal, it's the whole ring. So there exists A1, A2, AN in I, and B1, B2, BN in I inverse, such that A1, B1 plus A2, B2, AN, BN is equal to 1. I claim I is in fact generated so I love it when proofs tell you something because assuming that I did the rest of this right, what this tells me is you can generate that by any set of elements, AI, that can show up in an equation like this. And so to find sort of the least number of generators, you can just find the smallest equation with respect to n for which this holds. Okay, certainly. That must be x, right? Because all the AIs are in I anyway, so it's gotta be that. How about the other one? For other containment. Let alpha be an I. I've got to show that alpha, it can be generated by A1 up to AN. Any ideas?
Side the equation you got for one up there.
Okay,
Alpha B.
just be her. That's so much. Yeah, she was about to get you. So multiply this by the equation here. The alpha is, and let me write this sagaciously. Alpha B1, A1, plus alpha B2, A2, plus alpha Bn, An. And why did I use my Gandalf-like skills to write it in that form?
In order to, oh, because alpha times B1 is in R because all, FJ.
Alpha is in, or I'm sorry, the BIs are in I inverse. The BIs are in I. So when I hit alpha, which is I times, these are all in R. So alpha is an R linear combination of AIs. So alpha is in. Therefore, so I is A1, AN is 5. Okay, any questions on that? Okay, now I'm gonna up the voltage a little bit. This is one place where if you specialize, so here's what we have. We have that, if you just have a garden variety invertible ideal, it may not be principal, we've given an example of that, but it's gotta be finitely generated. Here is a local theorem, which actually is extremely useful. Theorem. Let R be quasi-local. So recall that just means there's a unique maximal ideal and I an invertible ideal. Of R, then I is principal. Okay. This kind of ups the voltage a little bit because in your quest, so I showed this at the beginning of the class. So here's like the worst way in the world to prove a theorem. At the beginning of the class, I gave you an example of an ideal that had two generators and was invertible, correct? So, theorem, that ring was not quasi-local, right? Because the theorem says any quasi-local ring, if you have an invertible ideal, it has to be principal. I gave you an example of a ring that had multiple generators, more than one, that was invertible. That ring has to have influencing maximal ideals. This is kind of a groovy little theorem because what it says is your hunt for things that are invertible should not go beyond the principal if you've only got one maximal ideal. Okay, let us suppose R is quasi-local and I in R is invertible. Yes, invertible ideals don't have to be contained in the ring R, but if I is not, if it's invertible, it's not in the ring, I'm just gonna push it down into there just by multiplying by a principal, and that's not gonna change anything. Everybody okay with that? So I'm gonna assume that I've got an ordinary ideal, inside of R that is invertible. Now, we now employ the previous. I know that this is invertible, so therefore it must be finitely generated. Previous, I is finitely generated. By say A1 up to AN. Well, actually, I don't even, I think that would just pop out of this automatically. Right. Say I is. Since I inverse is equal to R, then there exists B1 to Bn and I inverse such that, oh, how vector style points on board use, right? We should write that on comments or something. Right, so again, we have this same equation, right? Now, this is where we set things apart because of the fact that it's quasi-local. Notice that each term is in R, right? Because this is in the ideal, this is the inverse product in R. So at least one of these terms on the left-hand side of the equation must be we'll say that A1, B1 is a unit, A1, B1 is a unit of all without loss of denial. Why?
Because if every AI, BI is not a unit, then you can isolate, for example, A1, B1 equal to 1 minus everything else. And everything else, since it's not a unit, 1 minus a non-unit in a quasi-local is a unit, so.
Okay, yeah. So at least one of these has to be a unit. If not, they're all non-units, right?
Means they're all in the maximal.
That's right. If they're all non-units, then they all live in the maximal ideal, right? If each AI, BI is a non-unit, then each AI, BI is an M, the maximal ideal. There's only one maximal ideal, so there's only one to live with. Therefore, the sum AI, BI, one is an M, which is a constant. This depends very heavily on the quasi-local, right? Because if you have infinitely many maximal ideals, they can all live in a different one and sum up to one. But you can't live in different ones like that for this situation. Everybody okay? So we're going to assume that A1, B1 is a unit. So A1, B1 is a unit. And I claim that I generate by A1. Notice that it's totally true, right? So it suffices to show each AK is in the ideal generated by A1. Right, because that will mean A1 divides all the generators, so the ideal generated by A1 will contain I. And let's see if I can do this smoothly. Right. So let's write this way. Consider AK equals U inverse AK. Right? Which is U inverse A1 B1 AK, which is U inverse B1 AK A1 1. This is in R, as is this. So this is in. So every AK is divisible by A1, therefore A1 contains I as well. So A1 and the theorem. Any questions on this? I'm gonna take this one step further. I'm not gonna prove this, at least not yet. I might put it on homework, but here's a follow-up. And it will give another strong result corollary. 4 to yes. If R is semi-quasi local and I is an invertible ideal, of R, then I is principal. So you can bootstrap what we just did to the case of finitely many maximal ideals. That'll work as well. It requires more work. But as a follow-up, that means that the first example that I did today, actually, it not only is it not quasi-local, but it must have infinitely many maximal ideals. So the previous theorem is actually good for a finite number of maximal ideals. Any questions on that? Any questions? All right. Well, you all have a good day, and we will see you all on Friday.